A soldier crouches behind cover, heart pounding, sweat dripping. In 1 second, everything depends on a single pull of the trigger. The firing pin strikes, a tiny explosive ignites, gunpowder combusts, and in 3/10 of a second, a projectile launches at over 3,100 feet per second. But here is the thing, the real story is not in that split-second explosion, it is in what happened months before, in a factory where workers judge temperature by the color of glowing metal, where a speck of dust smaller than a grain of sand can mean the difference between a weapon that fires and one that jams at the worst possible moment. We are about to follow a single bullet from raw metal to finished round, and what you are about to see is one of the most obsessively precise manufacturing processes on Earth. This is how millions of bullets are made, the beginning of brass. Let us start with something that seems impossible. Picture a flat brass disc, about the size of a large coin. Now imagine a machine weighing as much as 3 elephants slamming down on it with enormous force. What happens next defies intuition. The brass does not shatter, it does not crack. Instead, it flows upward, like water filling a cup, except the entire time, it remains solid metal. When the press lifts, what went in flat comes out looking like a shiny shot glass. An operator grabs it and tosses it onto a conveyor belt. This unassuming little cup has just begun a journey that will take it through dozens of machines, multiple buildings, and quality checks so rigorous that a deviation thinner than 3 human hairs means rejection. But our brass cup has a problem, and if we do not solve it quickly, everything falls apart. That incredible pressure just did something dangerous to the brass. At the molecular level, everything is locked up. Think of it like a traffic jam frozen in place. Try to shape this brass again right now, and it will crack like frozen chocolate. So the conveyor belt carries our cup about 20 feet to something called the annealing furnace. Basically heat therapy for metal. Watch as it disappears into that glowing opening. The temperature inside reaches between 650 and 760 degrees Celsius, hot enough to make brass glow. And here is where human expertise becomes irreplaceable. The operators running this furnace do not rely on digital readouts. They have done this so long, they judge temperature by color alone, looking through a small window at the glowing metal. Cherry red means perfect, orange means overheating, dark red means too cold. 20 minutes later, our brass emerges, still glowing. It drops immediately into a cooling bath directly below the furnace exit. But this is not just water, there is citric acid mixed in. Yes, the same stuff in your orange juice. The acid eats away microscopic impurities, while special lubricants keep our future bullet casing from sticking to its neighbors. Our cooled brass cup rides the conveyor to the next press station. This machine does not just push down, it pushes our brass through a hole that is slightly smaller than the brass itself. Imagine squeezing toothpaste through a tube that gets narrower as you go. The brass has no choice but to get longer and thinner. What was a shot glass starts becoming something that actually looks like a bullet casing. But watch closely, it is glowing hot again just from the friction of being squeezed. So the conveyor loops it back through the same annealing furnace, then the cooling bath, then to the next press. This happens 7 times. Each press in the line makes the hole smaller. Each loop through the furnace and bath takes another 20 minutes. By the 7th and final press, our casing is exactly 5.56 millimeters wide. That is the NATO standard, officially adopted on October 28, 1980. And that dimension has to be precise because this ammunition needs to work in dozens of different weapon systems used by military forces around the world. But we are not done yet, not even close. Every casing comes out of those presses too long. Brass flows unpredictably, kind of like getting different amounts of toothpaste each time you squeeze the tube. A spinning carbide blade trims each case to exactly 44.70 millimeters. And when I say exactly, I mean it. The tolerance is less than the thickness of 3 human hairs. Any deviation and the casing gets rejected. Those trimmed brass spirals, they fall through a chute into bins below. Tomorrow they get melted down and become new discs. Nothing gets wasted here. Our trimmed casing now travels to a different building for cleaning. It drops into what looks like a giant cement mixer filled with what appears to be hamster bedding. It is actually something called corn cob media, literally dried corn cobs ground into rough granules. For 45 minutes, our casing tumbles around while these granules scrub away microscopic brass shavings we cannot even see. One invisible flake in the wrong place causes a misfire, which means a soldier's weapon jams when they need it most. Now, Now, while this casing tumbles in corncob dust, something far more delicate is happening in another part of the factory. Picture massive spools of wire, each one weighing hundreds of pounds, gray metal coiled like spaghetti that never ends, row after row of them stacked on industrial shelving, waiting their turn. This is lead, but not pure lead. Pure lead would be too soft, deforming the moment it left the barrel. It is alloyed with a small percentage of antimony, typically around 2% for military ammunition. This makes it just hard enough to hold its shape during flight, but soft enough to expand when it hits a target. That balance took decades to perfect. The wire feeds into a cutting machine that chops it into cylinders with mechanical precision. Each one weighs exactly 62 grains. And here's a fascinating detail that connects modern warfare to ancient history. The grain is a unit of measurement dating back to antiquity, originally based on the weight of wheat kernels. Medieval merchants weighed gold against grains of barley. Now we use that same ancient standard to build ammunition. Some things never fully change. A machine takes that copper cup with the lead core rattling around inside and squeezes them with 40 tons of pressure. Imagine the weight of several fully loaded trucks concentrated on an area smaller than your fingernail. The copper does not crack. It does not split. It flows like thick honey up and around the lead, wrapping it completely, conforming to every contour. In 3/10 of a second, two separate pieces of metal become permanently joined. You could not separate them with a blowtorch. They are now one object, bonded at a molecular level. But right now, our bullet looks like a copper mushroom, not the pointed projectile we recognize from movies and ammunition boxes. So it goes through a series of forming dies, each one more precise than the last. Workers sometimes compare it to a sculptor gradually revealing a statue from raw stone. The first die creates the basic cylinder shape. The second starts forming the point, coaxing the copper into that familiar taper. The third refines it further, removing imperfections invisible to the naked eye. By the fourth die, we are dealing with tolerances of 2/10,000ths of an inch. That is 50 times thinner than a human hair. Thinner than most bacteria. These precision dies cost hundreds of thousands of dollars and take months to manufacture. Engineers agonize over specifications, running computer simulations before a single piece of steel gets cut. And they have to be perfect. Make a die too small, and the bullet cannot grip the rifling in the barrel when fired. It will tumble instead of spin, and accuracy falls apart. Make it too big, and you could have a catastrophic failure if someone tried to shoot it. The chamber pressure spikes. Barrels can rupture. People can get hurt. The final die creates something most people never notice: the boat tail. Look at the base of any rifle bullet, and you will see it taper slightly, like the back end of a sports car. This tiny detail, maybe 2 millimeters of taper, significantly reduces air resistance. The air flows off the base smoothly instead of creating turbulence. At extended ranges, this subtle shape can mean the difference between hitting the target and missing completely. 2 millimeters. That is all it takes. Our bullet then tumbles for 20 minutes in a drum filled with steel pins no bigger than sewing needles. Thousands of them cascading over the bullet's surface, polishing away imperfections too small for human eyes to detect. When it comes out, the surface is smooth enough to see your reflection, shinier than jewelry in a display case. Because any tiny scratch becomes a point where air resistance increases, changing the bullet's flight path by fractions of an inch that compound over hundreds of yards. Every single bullet gets weighed to the 10th of a grain. A laser spins each one while measuring if it is perfectly round, checking for wobble. If it deviates by more than 3/1000ths of an inch, rejected. Into the reject bin it goes. Those rejects get a special treatment. A machine pulls the copper jacket off and recovers the lead core. Workers collect the separated materials in different containers. Today's reject becomes tomorrow's raw material. The cycle continues. The bullets that pass receive one final treatment, a microscopic coating of wax, so thin you cannot see it or feel it even if you tried, but it prevents oxidation during storage, sometimes for years or even decades. But even now, this bullet is only halfway finished. Coming out of the tumbling drum, our clean casing rides a conveyor through an air knife, a high-pressure air blast shooting straight down, moving at extreme speed, faster than cars on a highway. Anything loose gets blown into collection bins below. Not a single particle of corncob dust can remain inside. Then it enters a chemical bath. The exact formula is proprietary, a closely guarded secret, but workers say it smells like lemons mixed with something sharper. It strips away oils from fingerprints and leaves the brass cleaner than surgical instruments. Cleaner than anything you have ever touched with your bare hands. Now our casing enters the most dangerous part of the factory. This is where things get serious. A A primer is a tiny metal cup filled with impact-sensitive explosive, the stuff that starts the whole firing sequence when you pull a trigger. Each primer contains about 4.5 grains of explosive compound. That is roughly the weight of a few sesame seeds. It looks almost harmless, sitting there in its little cup, but it is enough to set off the main charge, enough to send a bullet downrange at 3 times the speed of sound. Watch how carefully the operator handles these primers. Her movements are slow, deliberate, almost meditative. They come in tubes of 100, and she places them one at a time into a feeding mechanism. The machine presses each primer into the bottom of our casing with exactly 38 pounds of pressure. Not 37, not 39, exactly 38. Too much pressure and the primer could go off right here in the factory. That has happened before, in other places, in other times. Too little, and it will not seat properly, causing misfires in the field when a soldier needs their weapon most. The operators at this station rotate every 2 hours, not because the work is physically demanding, because the concentration required is mentally exhausting. 2 hours of absolute focus, then a break. Fresh eyes, fresh mind, one moment of distraction, one wandering thought about dinner plans or weekend errands could mean evacuating the entire building. Everyone here knows the stakes. Our casing, now with its primer installed, moves down the line to the powder station. This is where our casing gets its main explosive charge. Exactly 26.5 grains of gunpowder, not approximately, exactly. The machine dispensing this powder is extremely expensive, the kind of equipment that costs more than most houses. It has to be, because the tolerance is unforgiving, being off by just 0.1 grain, roughly the weight of a single grain of table salt, changes the bullet's velocity by 20 feet per second. That might not sound like much, but at long range, across hundreds of yards, that small difference compounds. It could mean hitting your target or watching your shot sail wide by inches that might as well be miles. The machine drops exactly the right amount through a copper funnel into our casing. The funnel is copper for a reason. We will get to that. And here is something crucial that separates ammunition factories from almost any other manufacturing facility. No metal tools can touch the powder directly. None, because static electricity could set it off. The same static shock you get touching a doorknob in winter, that little zap that makes you flinch, could ignite gunpowder, and in a room full of explosive material, ignition means disaster. That is why everything here is grounded. The machines have grounding wires. The operators wear special shoes with conductive soles. Even the floor has copper strips running through it, channeling any stray electrical charge safely into the earth. Workers have to touch a grounding plate before entering this room, discharging any static they have built up walking around the rest of the facility. Once the powder is loaded, the actual bullet finally shows up, the moment we have been building toward. The machine presses the projectile into the mouth of our casing at exactly 2.260 inches overall length. The pressure has to be perfect. Too loose and the bullet falls out during shipping, rattling around in the box, useless. Too tight and the pressure spikes dangerously when fired, potentially damaging the weapon or injuring the shooter. Another die crimps the case mouth, squeezing it just enough to grip the bullet securely. Not too tight, not too loose. A laser measures our completed round for concentricity, basically checking if the bullet is perfectly centered in the casing, aligned precisely with the axis. If it is wobbling even slightly, even by amounts invisible to human eyes, accuracy suffers and the round gets rejected. Our bullet is now complete, but it is not done yet, not by a long shot. Before this bullet ever gets loaded into a rifle, it must first pass a series of quality control tests that border on obsessive. The first inspection is human eyes. Our bullet rides past workers who are looking for scratches you need magnification to see, dents that are barely visible, any discoloration that suggests contamination. They check 50 rounds per minute, 8 hours a day. Their reject rate, about 3%. Those rejects get pulled and dismantled, the components recycled back to the start. Our bullet passes and continues to the gauge station. Here it gets dropped into a piece of steel, machined exactly to match a standard rifle chamber. If it does not drop in smoothly, it fails. Next is the weight station. Our complete round should weigh 190 grains with a tolerance of plus or minus 1 grain. The scale is so sensitive it can measure 1/10 of a grain, about the weight of a human eyelash. Our bullet passes. Now comes the final step, the head stamp. A machine stamps tiny letters and numbers into the base of our casing. The factory code, the year of production, a standardization mark. This is like our bullet's birth certificate, tracking where and when it was made. If this ammunition ever causes problems, investigators can trace it back to this exact factory, this exact day, even this exact shift. In a few weeks, this bullet will ship to a military depot. It might get issued to a soldier tomorrow, or it might sit in storage for 20 years. Think about what we just witnessed. A flat brass disc transformed into a precision casing through 7 stages of extreme pressure and heat therapy. Lead wire chopped, jacketed in copper, and shaped to tolerances 50 times thinner than a human hair. Explosive primers handled with such care that operators rotate every 2 hours to maintain concentration. Gunpowder measured so precisely that the weight of a grain of salt matters. Tens of thousands of these produced every single day, millions every year, each one built to the same impossible standard. And all of it, every step, every check, every rejected round melted down and remade, exists for one reason. Because somewhere, someday, a soldier will crouch behind cover, heart pounding, sweat dripping, everything depending on a single pull of the trigger, and when that moment comes, the bullet has to work. Not probably, not usually, every single time. That is the weight of what happens in these factories. Ancient measurements, like the grain, dating back to when people weighed things against wheat kernels. Modern precision measured in 10,000ths of an inch, all converging on a single purpose. In the moment that matters most, there is no room for almost. What shocked you most about this story? Let me know in the comments. And if you want more deep dives into the technology reshaping our world, hit subscribe, because the next breakthrough, it's closer than you think.